So I'm Xavier VIGOUROUX from the Center for Excellence in Parallel Programming. This is not the Center of Excellence. So we are seeking for that. I don't consider we have it, so we are trying to move forward in the excellence. So this Center for Excellence has been launched in 2012. It's based in France, and I will describe what we are providing in this service. So my presentation is split in several parts. This is linked between HPC and energy. So there are different aspects, and the discussion that took place this morning demonstrated how linked are the energy and the HPC. In fact, it's much linked than what we thought. When you look at all the computations that are required for the climate change, when we are looking at the computation required for the batteries, for all the simulation, all these aspects, this is really huge. And the other way, this is really huge, the energy impact on the HPC in terms of constraints, because they are consuming so much energy that maybe the climate is being influenced by the HPC itself. So maybe it has to be included in the model they are simulating. So my talk is why HPC application services become key. This is very generic, and I like to be interrupted during my talk, so this is the way I enjoy the talks. Otherwise, I'm boring. So please interrupt me. This would be great. So let's make it very simple. For the first thing is that the hardware evolutions are no longer transparent for the applications. There is no way for that. It was the case during in the 20 years ago or 10 years ago, but now it's no longer the case. So we have to modify the code for the hardware. And what has been presented today and what has been talked this morning is clear that there are a lot of questions related to which hardware, is there only one chunk of software, will I optimize this software for kernel, for GPU, for all this stuff. This is really a nightmare as of today for the software developer. So this is why, in fact, my Center for Excellence exists. So let's go back just very quickly to the past. So the first thing is the end of the Denard's law. So the fact that the density of power exploded. So suddenly, even if we are shrinking the transistors node, there is a power density that is increasing, whereas the Denard's law said it was constant. So the result is that the frequency, the CPU frequency, stalled and even decreased, in fact. Today, if we are looking at a famous top 500 list, and this graph is extracted from the top 500 list, this is the average CPU frequency of all the entries. If you look at it, in fact, today, coprocessors are beside CPU, and the frequency who is defined in the top 500 list is the CPU frequency. Whereas we are closer to 1 GHz, and the computation is coming from 1 GHz CPU instead of 2 GHz, 2.5 GHz. So in fact, the slope is today decreasing slightly. Nevertheless, even if we have this constraint, there is still improvement in the node size for the transistors. And today, we are moving to 5 nanometers, and this has been announced by, I shouldn't say that, by IBM a few days ago. But this is they have prototypes with 5 nanometers transistor, very complex, and I think we are really close to the limits in terms of electronics. So the end of the road for the transistor is in 2021, 2022, and this is 5 nanometers. Then we have to find something else. This is the end of the road, considering the technology we have as of today. I don't say this is the end of the HPC road. I must be clear. And again, even if we are going down to the 5 nanometers, we will have 8 times the area will be multiplied by 8 compared to what we have today. And the question we will have, sorry, I tried to push it that way, but not enough. So the question we have is what we will do with this area. Will we have 8 more CPU, 8 more cores on the same die, or will we have to use it for something else? And this is what the ITRS, in fact, is trying to anticipate and to foresee. So the first thing is that we try to go elsewhere. We try to find post-CMOS solution. We have to find real technological rupture, and maybe we can move forward and increase the power that way. The other thing is that we may use this surface to really other stuff. And this is exactly what we have in our cell phone as of today. We have very different technologies linked in the same die, and technologies are today merging to each other. And the last point is that we will have, from my standpoint, we will have improvements in terms of process. We will have a lot of different alternatives in terms of SKU, what we will buy in terms of CPU. So when you will ask for hardware, we will have much more choices than what we have today. Just to give you an example, ARM is currently providing the IP of a core with different vector lengths, what they are calling SVE. So it means that when you are taking this IP and you are putting that in a die and silicon, you can choose which will be the vector lengths that you will request. And maybe you will have on the same die different vector lengths. You at least have the possibility to have different vector lengths. And then for your application, you can select which part you will use for which part of your application. And it's even more difficult for software developer to select the right one, to have the right algorithm. And we can merge many things like this. And one guy from Intel, I think it was almost 10 years ago, said that with the increase of the area, he believed that 10% of the surface, let's do it again. Every time we will double the surface of the area we have for when we are shrinking the transistor size, then this area will not be used for doubling the number of cores. This area will be split to be used by different applications. 10% of the gain will be used for 10% of the applications, and 10% of the other gain will be used for 10% of the applications. And if you look at today the Skylake with the FPGA, this is exactly this spirit. We have a FPGA side by side with the x86 core, and to be honest, the FPGA is not used by many applications. But 10% of the application or 10% of the time of your application may get benefit from that. So some routines may be moved to this surface. And if we are generalizing this aspect, we are moving to this kind of architecture. Many architectures, many things merge in the same on the same die. And it will be a nightmare again to use that. ITRS again. ITRS. This is a copy from ITRS report, and we can see the maturity of the different technologies. So from the silicon photonic at the top, and from high radix networks, etc. Some are already ready. If you look at the 64-bit ARM process core, this is ready. So today there is no question. We have on-die power sensors here, not for HPC for this one, and obviously we have the 3D stacking through silicon via. So we are moving to that for a couple of years ahead. So let's see now what could be the impact on the application. So the first thing, obviously, the first issue we have to manage is the problem of scalability. So we have many graphs about that. We have many projects funded by Europe to try to tackle these aspects. For instance, in climate, in weather forecast with ESCAPE, with ECMWF, or EasyWaste by DKRZ in Germany. We have obviously the data issue, the fact that we have a number of cores, we have some allo that may be exchanged, we have to manage all these aspects. This is well known. Okay. As I mentioned, the issue will be the heterogeneity, the fact that we will have a multiplication of architectures. We can speak about CPU itself, GPU, many core, ARM, FPGA, and even DSP. Some people are talking about DSP. So I did one test in my team. I took an n-body simulation and asked each of my guys to port it on CPU, GPU, many core, ARM, and FPGA, just to see where we are. Some are very good in terms of productivity, some are very good in terms of performance, and there is no one unique choice. This is the 10% of surface, and for 10% of application, this is exactly what I mentioned. And we have to decide. We have altogether. Oops. Yeah.
Yes, portability, productivity, performance. What about energy?
This is a constraint. This is another dimension for me. I agree. We will. This is a good question. I will go through that direction at the end. And you have seen my presentation, maybe.
So for the n-body problem,
yeah.
Which of these perform best?
For this version, this was the GPU.
GPU.
Yeah, far ahead. Far ahead. But again, we have to see the worst picture between the performance, the productivity, and the portability. Because obtaining a very efficient GPU program is very difficult. There is no dotted line to follow, so there are some tunnel effect, and this is tricky. And we mustn't mix portability, productivity, and performance. For me, there will be trade-off to be found. How if you are seeking for pure performance, you will not have a portable software. For me, you will have to realize we will have to layer the software to have the performance libraries, and then we are abstracting on the top of these libraries to have more portabilities. But we really have to see where will be the cursor.
Then I have another
element.
What about maintainability?
For me, I put that on the productivity. Okay. Debugging, how long it takes to generate a new version. This is for the FPGA, for instance, and the maintainability, the fact that how many developers are able to modify the code and to understand the code. This is also something that put in productivity.
Yeah, because so with the computer scientist approach, what we call maintainability is different than what is required by physicists.
Yeah.
So code base are used to be used for decades, or developed for years before you can get the first scientific result. So maintainability for them is much harder than what we call maintainability as
but
scientists.
This discussion took place for a long time with the DSL and try to find these solutions. If you look at Fortress, for instance, for the HPC program a few years ago. And for me, this is something to seek, but it's very hard, I agree. So, microarchitecture, this is also an issue. This is exactly what I said. Today, if you look at the vector length is increasing, but at the end, if you look at AVX 512 that we have today, what will be the real benefit for the application? I did one test for one application. I get between the vectorized version and the non-vectorized version, I have 5% difference. So and we don't need to go further. And the microarchitecture improvement for me, there will be not that much. So don't think your application will go faster on the next generation. You will get few percent increase, but not that more. And one very important point. This is the time variability. For me, this is something we have seen for the turbo mode a few years ago. If I take a program, okay, this is the duration of a program, really pure CPU program. Outside, this is 38 seconds for the run. Inside, this is 28 seconds for the run. Okay, so this is faster here than here. This is a low frequency. This is medium frequency, and this is a turbo mode. And this is each core, okay, each core of a node. And you can see that this is and this is reproducible, okay? So every time I will run the program, I will have this curve here. So the three curves is the mean, the max, and the mean. So this is nodes, okay? Each node has different cores, and then we have the average power. Here, the turbo mode, you don't get the same duration for the same code combined with the same vector length. And if you do some barrier between them, then you will waste your time. And what is occurring here, a few years ago with the turbo mode, will occur today in the new generation because of the TDP and because of the energy management. the silicon under your feet will change the frequency. It's big. It depends on the generation, but for instance, if one core was doing a vectorized operation beside you, it was limiting your own frequency. So if you are doing a computation which is heterogeneous, then you will have issue will be slowed down by someone else, and it creates some underdeterminism. And this is a real issue today. Is that if you have some numerical precision, if you need numerical precision, the order of your operation will be important, and then you will not be able to get the same result. So you will either you decide you are saying the precision is enough. This is numerical noise, or you say I want to be sure that every time I will run the same code, I will get the same result. And this is two trends we have to go. Okay.
Excuse me.
Yeah.
About your last bullet point, applications must be less tightly coupled.
Yes.
Actually, it's a kind of wishful thinking, isn't it? Because I mean, our applications are what they are. I mean, the physics is what it is, and certain problems need, like all-to-all, basically, in the end.
All-to-all is.
All-to-all in the sense that the physics problem you need to solve at each time step, say a boundary value problem, global problem. So this means everywhere there must be some sort of data which has been communicated through your system. So
if your problem.
So my question is the architecture going to dictate the type of physics we're
No.
going to be able to or it's a bit provocative, but it's of course for discussion. Or is it the other way around?
There was a workshop about who is lagging behind, in fact, between. And if you look at today's architecture, just to give a very simple example, if you look at today's deep learning impact on the architecture, if you look at the GPU or the Xeon Phi trend, you will see that there are some features are appearing not for HPC because it just appears because of the deep learning. So this is a constraint somehow. You will have much more power in single precision than in double precision. So your decision as a developer will be which one I will choose. So you will have constraints. The hardware will put constraints on the software, and this is clear. The fact that you have some problems, physical problems, they are real. Okay, this is reality. But if you look at the FFT, for instance, this is clearly something that will not scale. There is no way the all-to-all, the way the communication are exchanging to each other will not scale. We have to find other solution. And if there are some way to see there are different approaches to the same problem. This is why this is interesting. Some software are very efficient for today, but they will decrease. Another one will appear. Stochastic simulation are appearing again, for instance, because you can multiply the number of trajectories. So you can see the way you are solving your problem, the algorithm you will use will be constrained by the hardware. But I agree that this is not dictatorial.
I mean, so to complement maybe your answer, maybe there is different types. So all-to-all, yes, okay, that's the physics that dictate, but we are using also programming models, so to speak, of an MP with a fork-joined model. So at some point you have all the threads that are doing the same thing, and then when they're finished they have to synchronize. Yeah. This you could avoid with other programming paradigm like task-based programming models. So here you already release a bit the tightly coupled notion of your application just by using different programming models.
And there are task-based way to implement things with some direct acyclic graph that maybe optimize some runtime. There is some work has to be done on that side also. Moldable applications and malleable applications are much more efficient in terms of resources than just booking a full set of nodes for the whole run. So we have to find a way to make something more dynamic, in fact. Okay. I will move forward. This is great. I don't know how I move this that way. Yes. Okay, so all these things will impact the application. You understood. So we are clearly the work has to be done on application, and the Center for Excellence I'm managing, in fact, is focusing on that, trying to provide different. This is very close to the Center of Excellence, the ECHO of today. So providing trainings, application performance, hardware access, and optimization. I have one key advantage compared to the Center of Excellence is that I am an integrator, hardware integrator. So I have some knowledge about the roadmap, Intel roadmap or NVIDIA roadmap or ARM roadmap that helps me to decide for the future, the coming years. This is the only key advantage. So when I'm doing I may do a modification, I know what will be the benefit from the excess. That's the only benefit I have from you. But many customers have, or many institutions has worked with us, in fact. So you know some of them clearly. There is a huge discussion about Bull and Atos. So Bull is a company that has been acquired by Atos in 2014, but Bull will be a trademark. It will still exist. So we can say Bull, an Atos company, or we can say Atos. Bull is a better name for the activity I have today. And Bull has provided this kind of hardware. So this is what we are calling the Sequana. So this is a huge, it's more than 2 tons 6 machines with direct liquid cooling. So we have 288 nodes in this side, and each node is on a blade like this, and this is warm water cooled. So this is cooled with 40 degrees water, which is enough to cool down 70 degrees CPU. And this is, in terms of energy, if we are speaking back to the energy, this is much more efficient to cool with warm water than what we have done before, when we were consuming 80% of the energy for the cooling. Another aspect of Atos of Bull development is what we are calling extreme factory. If I have the hardware, if I have someone to optimize the application, then I can host that somewhere, and then I can. The thing I have to do is just to provide access to these resources. Today there is a huge evolution in terms of industry. The fact that they are starting to offshore their applications. A huge French car manufacturer, for instance, decided to outsource every compute power to Atos. We just have a link with from their factory to this solution this one, where there is only a cable. So the engineers on their side are just pushing some jobs in the evening. They just want to have the result the day after. That's all. We have 8 hours to do the computation. When I coming back in the morning, everything must have been computed. And this is the only question they have. So today, HPC is really something key for the academic, but this is also key for the competitive advantage. In this case, this is crashing the cars. So
this you're saying is a dedicated HPC for this kind of industrial applications?
So, in fact, we have for the case of the car manufacturer, they have a direct access. They have, in fact, some ISV they are relying on. So we have a partnership between the car manufacturer, ISV, and us to provide something transparent. This is the fact that the computation is elsewhere is transparent. But for the usual case, we have we have a portal like this one where people are just submitting their jobs, and this can take place. The job can take place transparently, either on premise or hosted or on the cloud, in fact. And
And how do you do it? I mean, they pay something?
Yeah. It depends.
Yeah.
It depends on the contract.
What is the model?
They can if this is on premise, this is their own hardware, so they are just paying for the license of using this portal. And then when they are extra load, they are overload on their workflow, then they can ask for extra extra power, compute power, and then this is the contract that will say how much power you will have, what is the license system, etc. And clearly agreement had to take place with the ISV in this case. Okay, so this is for the. Okay. I will do it quickly, but this is something I like, so I have to. I will do it quickly. Today, if we look at what has been optimized in terms of energy and power consumption, we can say that most of the work has been done. Cooling was costing 80% of the energy before. 80%. It was adding 80% of the energy. Today, this is 8%. We have the batch scheduler, which is managing all the way the applications are spread on the supercomputer. The alimentation is okay. C-state, CPU C-state, everything is managed. If you look at it, everything is managed now and optimized. So the question is, what more can we do on that? And for me, the solution is to have a global consistency. And when I say global consistency, I mean with all the line from the energy provider to the result. Today there is some kind of disconnection, and I am speaking to people. I think I will have a lot of interaction with you. For me, we have to find a way to not to waste energy, or to try to have from the energy provider, from generation, from the CPU, having a way to tight effectively the way the energy is coming from one side to the other. For example, if we look at the way the machine is working today, we can say that the cost today the cost of a run will depend on the cost of the energy. So today, why shouldn't we could have a policy for the batch manager in such a way that some application will run when the energy is low and some application will run when the energy is high. And if the application is efficient, we could say, okay, I agree to use this high cost for you because I know your application is efficient. When it's not efficient, I say, okay, you will wait. We can have the same thing for the CO2. We can have the same thing with the weather. So if the cooling is consuming a lot of energy, then because there is no free cooling, then we can sell it. So for me, something I'm proposing and something I'm pushing today in the software development is to define some application quality. The application quality is the fact that an application is using my energy efficiently. For instance, if I use an application with 64 cores, and if the scalability is poor, then I don't want the user to launch this same application on 128,000 cores because it will waste all of my energy. So the goal is to try to assign this vignette. I don't know the English word, I will say vignette. The vignette, these vignettes are used by cars in France. So, sorry? Token, yes. These tokens are used by cars in France. The previous way to select the cars when there was high pollution in France was just by the plate. Do you have an odd number or an even number on your plate? Then you were able to run, to drive or not to drive. I have an electric car, okay, a full electric car. So 50% of the time I was not able to use my electric car, but I was able to use my diesel, which was an even number. This was a previous version. This version is not that good neither, because today I have one car here, one car here. The issue is that the size of the engine and the real pollution is not taken into account, but that's a better way to use that. And I want to apply the same thing for the energy and the efficiency of the applications on the supercomputer. At the beginning, the criteria will not be that great. So, what is the scalability? How do I evaluate that? This really something difficult. But at the end, I would like to have the resource manager taking that into account. A scientist will always will require his result as soon as possible, even if it consumes twice the energy. I will have my results 3 seconds before. I don't care. I will launch it. With this kind of solution, I will say, with 128 cores you are here. With 64 cores you are here. You will have more priority on this with this token than this one. Then the scientist will prefer using this one. So this is some kind of incentive, and I am pushing today to do this kind of intensive. This is something evolving, but I have one hat in Atos, which is trying to define the product for the energy, and this is something I'm pushing today. Yes?
Maybe, I mean, you're pushing the energy efficiency, which is okay,
But from the software.
yeah, but isn't this proportional to the scalability? Is it something other that I'm missing? Isn't the scalability, isn't it the same, or?
It can be the scalability. It can be that the fact that you are relying on a good library. For instance, if instead of implementing all the time your matrix multiplication, then you can rely on the GGMM that has been optimized. And okay, you will get the token number 4. So this is all this kind of. Today, I think the only way, even if I'm pushing to have an automatic way, okay, to assign this token, I think it will be tricky. Maybe artificial intelligence, deep learning will help. But for me, there should be a group of people just assigning the token that for each application.
I got an idea related to this.
Yeah?
I think how much things are lost and how people is so optimistic about their codes. I mean, a good idea would be to say my code is number 2. Yeah, and that would mean that when you go to praise, you have a priority. But that would also mean that if praise people come and get you code, they can't optimize it more than 10%. If you say that it's 2 and they come and they optimize it 10 times, then you will be putting condition 5 for a long time.
So this is why, who is the organization who will assign this token?
Praise, I guess.
Yeah, maybe praise. But you know, I'm pretty sure.
It's still nothing close to that is being done, and lots of resources are being spent.
Yeah, I'm pretty sure that even with this, the way to assign this token must be safe enough for scientists not to use it for another program, for instance. Oh, I have the token for this program, I will use it by renaming my binary and use it on the other one. So we'll have to be very secure. So, but this is something ongoing, and I think, okay, I will move directly to the conclusion because I'm late, and this is just this one. Not this one, this one. For me, there is a lot of improvement that's still to be made in terms of energy, efficiency, energy application. We have huge improvement today in terms of software development and fitting, co-designing, etc. But we have to think globally. This is for sure. But also there is another aspect, which is that everything has to come to an end. And the example I provide usually is the Concorde and the airplanes. It's not because they are not going faster today. They are not going faster. We are crossing the Atlantic even slower than what we used to be. But nevertheless, there are still improvements in terms of energy, in terms of usability, and all that cause that make it possible. That the improvements are going on today. And for me, the HPC, this is really the question. The question is, why do I think there is a typo? Sorry. Why we should have this increase in terms of power? What is power today? And is it the only criterion? Okay. Is it usability? That would be the one. Is if we have an exascale machine, in fact, how we will use it? Maybe we will use it with ensemble runs. There are different ways. What will we do with this exascale machine? Maybe it will be less reliable So how we will manage that? What will be the runtime? This is real question. I'm from Atos, so for me, I have to push the hardware. I will provide the hardware. But this is a real question of what we will do with this machine. There are huge challenges that will be solved with that. For sure, there are exascale challenges. There are some applications that will rely on that and that requires that. But for all the other people, what will be the benefit, maybe, from this machine? This is really an open question. I have no answer for that. And I don't know if you know this guy from Colorado who has a very amazing video in terms of arithmetic, population, and energy. And if you can just write down his name and listen to this video, it was in 1968 or 64, and this is amazing for that. Okay, thank you.
Thank you, David.